All right, so let's start the class. Today's topic will be on directional derivative. All right, let's begin with a function with in two variables. So here's a function f of x, y, okay? And it's defined in the domain, some domain here, okay? And then there's at the point, and we pick up a point. Now, the function is in two variables, okay? But we can also consider the restriction of the function in that direction, okay? I take let u to be a and b, so that's a direction. Given that direction and attach the point, then you have a strict line, right? A strict line. Along this strict line, if the function restricts to this strict line, then you get a function of one variable, okay? So let's find out how does, what is the rate of change of the function along this line, okay? And how to define it. Right, so this is the value. See, at every point here, this is a point, arbitrary point x and y, right? We know that x is going to be x naught plus at, y is going to be xt, right? This yt is going to be x naught plus bt, okay? So the restriction for f to the line, okay, is a function of a t, okay? Is a function of t. I can is a function of t that's actually is going to be x of t, y of t, right? Okay. Then we can talk about the rate of change of the function along this line, okay? So the rate of change of the function along this line, okay, this is going to be, then you can get a derivative, right? So differentiate this, right? When assuming the function f is differentiable, you'll get x of t, y of t, then x prime of t, right? By the channel. And that y, x of t, y of t, and the y prime of t. That's by the channel. So at that particular point, you can set, let t to be 0. Let t to be 0 is a derivative. This is a place where t equals 0. At the point x not y not, right? So that is going to be fx. And the derivative of x prime of t is just a. So it's a plus, and that's b, okay? So this one, okay, tells you the rate of change of the function, the rate of change of the function along this line at time at t equals 0. So this is called, it is called directional derivative of the function in the direction of u at that point, okay? So, so we're going to introduce a new notation. So this is a new notation, D, capital D WF, okay? And we also put x naught, y naught. That's defined to be okay. And this is it is called the directional derivative of f at the point, okay, at that point, but in the directional of u, okay. We assume that the function f has partial derivatives. Otherwise, you cannot express in that way. You just look at the derivative, okay. So f prime is 0. Okay, this is also equal to f prime is 0. Okay, so if the So this is also a formula actually for the directional derivative of the function in that direction. Okay, so the original definition should be just f prime 0. Okay, then now if the function is differentiable, then you can express f prime phi prime 0. Okay, can be expressed in this form. Okay, so we have to assume that f is differentiable at the point. Otherwise, you don't get this formula, differentiable. Okay, f is differentiable. then you have this. Okay, then you have this formula by the chain. So we're not going to, so in some, well, we can use a limit to define directional derivative because f prime 0, this one, okay, is going to be, see, this by definition, right? Let's see. Let me give you the original definition, but it's not very useful. That's why we just use a formula for that. So the derivative, the directional derivative function at this point, right, is going to be this, right? And this is going to be, okay, 0 plus h minus 3, 0, right? Okay. So when you look at our definition for the phi of t, this is nothing but, here's f, this is just x naught plus ah, right? And then y naught plus bh. And the second one is f naught, y naught, okay? So that's the limit, okay? If you do not assume the function is differentiable at that point, then you can only use a limit to give the definition of directional derivative, okay? So this is our original definition for directional derivative, okay? Now, meanwhile, I also get a formula, right, for the directional derivative. If the function is differentiable, okay, if the function is differentiable, then it's given by the above formula, okay. All you needed to know is just a partial derivative of the function and the boundary, then this linear combination, okay. This is going to be the formula. But you notice that the partial derivative of the function is also directional derivative, okay? In fact, okay, if u is going to be the I, which is 1 and 0, okay, then the directional derivative of the function f is just this partial derivative with respect to x. The reason is, look at a is going to be 1, b is going to be 0, okay? If u equals j, then the partial derivative of f, and the direction derivative of f is just the partial derivative function at that particular point with respect to y, okay? So, so you get a general formula for the directional derivative. And actually, the direction derivative depends on a and b linearly, okay? In general, right? In general, for a general vector, right? For general vector, I'm going to rewrite this in a slightly different way. So I still write down the formula again, okay? Okay. Now this is just actually it's a linear product, the inner product. So this is there is another notation, A and B, okay? And this is the inner product, right? Dot product sometimes called. So this is a U, okay? What is that? The combination, the vector defined by those two partial derivatives. We can introduce a notation. This is called a gradient of the function in that direction, okay? So this is just equal to the dot product of these two vectors. All right, so all you need to do is find this so-called the gradient of the f. Okay, at the point. Let's take a look at some functions. Okay, here's a function, h. Let's look at some examples here. This is x squared minus y squared, okay? And the point is just the origin. Okay, the graph is a pretty strange graph. Okay, it's not easy to draw this graph. Okay, you can draw the graph. Yeah, the function somewhere is negative, somewhere is positive. Okay, so if you draw the graph, this will be yeah, it's not easy to draw the graph here. This is x-axis, this is y-axis, this is z-axis. Okay, so the graph of z equals x squared minus y squared is not yeah, it's not easy to draw it. Okay. Now when I think it's going to be like that. Okay, when x equals 0, you get a line like that. Okay, when y is 0, it's going to be like this. So this is looks like that. Okay, that's a picture. Okay, you can sit on that. Okay, there's a center point. Okay, so that's a picture. Okay. All right, so let's find out. Let U to be an arbitrary vector. Okay, let's find out the direction derivative. Okay, at that particular point. Okay, so all you have to do is find the partial derivative. Okay, that's going to be 2x, right? And partial derivative of this is going to be negative 2y because the first term is x squared, then you differentiate the y squared is 2y, so you have a negative sign. Well, the interesting happens this gradient, okay, at the point 0, 0 is going to be, right? We just needed to find this vector called a gradient. So it's going to be 0, 0. It's trivial vector, it's a 0. So since this is going to be 0, so therefore the directional derivative, it's really independent of the direction. It's always equal to 0. Okay. And yeah, it's always going to be 0 at that particular point. But if you choose another point, okay, if you let it be like a 1 and a 2 at this another point, okay, then the gradient of the function at the point is going to be when x equals 1, that's 2. When y equals y equals 2, that will be negative 4. Okay. Then the directional derivative in that direction, okay, is going to be 2, negative 4, dot a and the b. So it's 2a minus 4b. So this depends on a and the b linearly. And you will see that this linear function, it's not always positive, sometimes negative, sometimes positive, sometimes 0. Okay? Sometimes 0. So there will be a question when it has a maximum value. Okay, of course, when a, b are very large, this can be a very large number. So you have to restrict it to the unit of vectors. Okay, if we use a unit of vector, what is the largest possible value for this function, for this derivative? Okay, this is a question we're going to discuss later. Okay. All right, so now let's let's look at another problem. Okay, so we have a f function. It's two variables, x cubed minus 3xy plus y cubed. Okay, plus y squared. Okay, just like this. All right, we want to find out the derivative, the directional derivative, okay, at the point when the two in the direction, okay, in the direction, this is the direction, let's use a unit factor. So this is going to be 1/2 square 3/2. Okay. So the picture, it looks like that. Okay, here's a point 1 and 2. Okay, the direction derivative is going to be this. Actually, all the unit vector form a circle. Okay, this angle is going to be pi over 6. Okay, so that direction has components 1/2 and the square 3/2. Okay, and I want to understand how does the value function change along this line in that direction. Okay, that's the geometric meaning of the direction derivative. The function restricted to the line. Okay, then you can see that's like a one variable function. Okay, and you want to know the rate of change of this the value function along this line. Okay, so you end up with the directional derivative. Okay, the derivative in that direction. Okay, now all you have to do is find the partial derivative, right? You get 3x squared minus 3y. Okay, the partial derivative with respect to y. Again, negative 3x plus 2y. Okay. Yeah, plus 2y. Yeah. So at that particular point, let's evaluate 3 dot square minus 3, and the y is going to be, yeah, the y value is just 2, okay? Right? So it's going to be 3 minus 6 is negative 3. Okay, that would be negative 3 times 1, when x is 1, plus 2 times 2 times 2. Okay, so that would be 1. Okay, so you got the partial derivatives at that particular point. So the directional derivative in that direction is going to be the gradient. Let's just put the gradient here, right? 1, 2, dot t. Okay, so the gradient first component is negative 3, the second component is 1, and this will be 1/2 square 3/2. Okay, so just the that's the dot product, negative 3/2, and plus square 3/2. Now you cannot simplify further, maybe just express in that form. Okay. So that is going to be the directional derivative. In this case, actually, is negative. Negative means the function along this line in the direction u. Okay, at the moment passes that point, the value decreases because the derivative is negative. Okay, this is just the derivative or restriction of the function along this line.
Would you mind explaining what you did in the very, very last line?
The very, very last line is this one, right? This is the very, very last line.
Yes, yes. What
Okay.
happened? How did you come to this from the previous line?
How did I come to? Okay, this is a dot product. Okay, that's a notation. If you have two vectors u, like a u1, U2, V, V1, V2, okay? So dot product is just U1 times V1, U2 times V2. That's just a notation. So when you see U1 V1 plus U2 V2, this can be written as dot product. That's called also inner product in linear algebra, okay, of these two vectors. So in my notation, remember, right? Remember, this is the formula says this is going to be A, right, plus B. So this is the sum of the two products. So this can view the V1, U2. That's considered V1, V2. Okay. Yeah. So you can rewrite this expression in the form, right? And the dot product A and the B, but the vector with component A and B is denoted by as U. You know, we at the very beginning we already given that U equals this, and this one we denoted by this notation. Okay, and this is called the gradient of the function. And just, you know, when you write the formula, we don't want to put all the details there and simplify it. So this is simply written in the form. Okay, so that is a formula for the directional derivative. Okay, this basically is the inner product of two vectors. The one vector is the direction, it's U. Another vector comes from the F. Okay, just the vector formed by the partial derivatives. All right. Okay, so all I have to do is find the so-called gradient, then write down the dot product, then we get the direction derivative. Here's a here's a function f x and y. You get, let's use it's x squared y cubed minus, it's minus 2x, for example. Okay, and we want to find out the directional derivative f. Okay, at the point, at the point of -1 and 2. Okay, in the direction of U. Use 2 and 1 with components. Right. So all I have to do is just find the gradient. First, you write on the formula. Okay, by the formula, right? This is a gradient of f at the point, right? And dot product was U. Okay, so you just needed to find the gradient. Okay, so vector U has component 2 and 1. This is a formula we have, so you write on the formula. All you have to do is find the derivative. I have to find the partial derivative of the function first, right? And this is going to be 2x y cubed minus 2. Another one will be just a 3x squared y squared. Okay, so now I can write down the gradient. The gradient is the value of the function, partial derivative at -1, 2. Another one will be, okay, then you evaluate each of them. I got 2, -1 here, 2 cubed minus 2. Okay, the second one is just 3 -1 square and the 2 square. Okay, so let's simplify. 16 minus 16 section is negative 18. Okay, this will be 12. Okay, so that is the gradient of the function. Okay, it's nothing to do with the direction. It's completely determined by the function. Okay, then you have like that, right? By the above formula. So what is u? U is 1 and 2. Okay. So now you write down the dot product, right? The dot product is the product of those two numbers first, and then those two numbers. Okay. Okay. So it's going to be negative 36 plus 12 will be negative 24. So that is the direction of the derivative. Okay. For function with the three variables, you can also you can get the formulas in a similar way. Okay, a function is three variables. So if a function is three variables, yeah, for a function for three variables, you can also talk about direction derivative. Okay, so consider function in three variables. Okay, and then now I have to draw the picture because it's 3D. Okay, this is the direction of u, a, b, c, right? So the directional derivative, first of all, by definition, okay, is going to be the limit of the value, okay, this along this line, and this is the h equals 0, here's the h equal, yeah, just h, arbitrary value, right? So the value of the function will be x naught plus ah, right? And bh is z naught plus ch, okay? So we look at the difference and divide by h. So that's the definition of the direction derivative. Okay, so origination, if the limit exists, then you can say the direction derivative exists. The direction derivative exists does not mean all the partial derivative exists. Why? Because this is only about the smooth, about the function along this line. In other direction, maybe the function is not differentiable. Okay, that's why we have to assume the function is differentiable at that point. Maybe it's differentiable in all the direction, including the x-axis, y-axis. So what you get, the partial derivatives with respect to x and y. Okay, so under the assumption, okay, so if f is differentiable at this point, means it's differentiable in all the direction, then you can have this formula. Okay, and again, we are going to introduce a simple notation for this. This is going to be called the gradient of the function and the dot product with u. Okay, so u is has components a, b, c, right? And this consists of three components. Those three components put together, then you get so-called gradient of function. Right? Right, so this will be three components. Yeah. Many terms, A, B, C. Okay. So those are the so you get very similar formula end up with when you differentiate, if the function is differentiable. Okay, then you can use that to compute a directional derivative. Okay. Now sometimes we simply write this part if we don't want to mention the point. then if you don't want to mention point, we simply read, yeah, without mentioning the point, okay, yeah. Okay, we can simply write this. Much faster, right? And this also can be written in the form like that. Okay. Yeah. For simplicity. Yeah. Then we don't need a, yeah. Sometimes we don't want to mention the variable. So the gradient of the function, yeah, is called, the gradient of function is just the set of partial derivatives. Okay. And this coming from the directional derivative. That's why we will put together, you know. And we will understand the geometry meaning of this later, okay? So let's find out the gradient function for the following function, okay? So given f, okay, x, y, z is going to be x, y, z, just the product of those three variables, okay? Find the gradient of the function. So this is a vector, actually. Okay? All you have to do is just find the partial derivative. And when you differentiate with respect to x, you get y, z. When you differentiate with y, you get x, z, right? When you differentiate with respect to z, you get x, y. So the gradient of this function is going to be y, z, x, z, x, y, okay? And there are many ways to express it. Now, if you take x, y, z out, you will get 1 over x, 1 over y, 1 over z. It's interesting, right? Yeah. Okay. Yeah, this is just a number times each of the component. You end up with yz, xz, and xy. So that is a gradient of the function. So the meaning of the gradient of the vector is actually, you can tell, yeah, this is the geometry meaning of the gradient is the normal vector to the level curve or level surface, okay? The geometric meaning, okay, of the gradient of f is the normal vector to the level curve, if in two-dimensional, or level surface of the function, depends on the variable, okay? Now let's understand why this is true. Okay, so I'll give you a simple explanation. So then you understand the geometry, okay? So take a look at, consider f of x, y, okay? So the level curve is this, okay, at the point x naught, right? Okay. So this is f of x, y equals k. All right, I'm going to, this is a curve, right? So I can express this curve in the using the parametric equations. Okay, so that means f of x of t, y over t is going to be always going to be k, right? No problem, right? So you parameterize this curve using the parametric equations. Okay. Then I differentiate both sides with respect to t. Okay, the right hand side 0. The left hand side by the chain rule. Okay, at that particular point, this is a t equals 0. So I can set the point, then this is nothing but the point. When you differentiate and you set t to be 0, we get this. Okay, and then here you have this. So it's going to be 0. Now, what does that mean? This can be written as a dot, the dot product. Okay. All right, so this is a gradient. Now, what is this vector? This vector is going to be tangent vector to the curve, to the level curve. So the tangent vector is this one. Okay. So it tells you those two vectors are perpendicular. So that means if I draw the picture, this is my gradient. Okay, this is a tangent vector. So this is a tangent vector. If yeah, so this is right. So they're perpendicular. So that implies the gradient is a normal vector. Okay, so that is this implies this implies gradient is perpendicular to the level curve. Okay, that's a geometry meaning. Right, so it says this is a gradient. Okay, so you know what is the gradient right now. Okay, but let's take a look at some examples. Again, I find we already know how to find the directional derivative. Okay, we just want to now find the gradient. Okay, given function x e to the y. Okay, find the gradient of f. Okay, find the gradient of at the point 0, 2. All right, so let's find out the partial derivative. It's going to be e to the y. Okay, and you differentiate with respect to y, just x e to the x times e to the y. That's still same. So just use the algebra. Okay, you don't need to understand the geometry, then just write down the formula, right? So it's 1, 0, 2, and when x equals 0, y is 2, this. When x equals 0, y is 2. So the answer is e to the 2 and 0. Okay. So this is a directional. This is a gradient. Okay. So if you draw the picture, yeah, we can draw the picture. You know how does it look like? Okay. So at the point, at this particular point, oh, yeah, the level curve passing through that point is going to be fxy. Okay. This is a f0, 2. It's going to be 0 e squared. It's going to be 0. So this is a level curve, okay, passing through the given point. The level curve passing through this point is going to be x e to the y equals 0. This implies x equals 0. So it's nothing but it's a straight line. This is the y-axis. So this is the level curve. Okay. The gradient is in that direction. Okay, the gradient. This is a gradient of F. Okay, so it's perpendicular to the level curve, right? It's a 90-degree here. Okay, now when how about the other level curves? Other level curves, if it's 1, right? If it's 1, then x is going to be e to the negative y. X is e to the negative y. When y is negative, yeah, when the y is 0, when the y is 0, x is 1. Okay, it goes like that. When the y is, let's see, this is the y-axis, when opposite direction. So, okay. When the y is 0, x is going to be 1. So this is a level curve, okay? Okay. When it's negative, this goes like that, okay? X e to the y equals negative 1. So I'm pretty sure there's a family of curves, and in the middle there's a vertical line, okay? Okay. Now the gradient at the other points must be in that direction. Okay. Okay. Looks like that. Okay. It's a perpendicular to the curve, to the level curve. Okay. Our next problem is about the maximum value of the directional derivative. Okay. First, we have to understand. The meaning of this, the inner product, and then we can talk about the maximum value. All right, so let's consider two vectors. Okay, two vectors. I have to use a u and a v. Okay, given two vectors. Okay, this is a u. That's a v. Okay. The dot product. Okay, divided by the length of u and length of v gives you the value of cosine theta. Okay, I hope you remember this. So you will get, right? Now we assume, okay, we assume that the vector v is going to be, vector u is going to be 1, okay? It's a unit vector. Then you will get u dot v is going to be cosine theta times v, right? Yeah. Okay. And we know cosine theta is always between 1 and a positive negative, right? So that's why the largest possible value you will get is absolute as the normal v, the length of it. The smallest possible value you can get is always negative v, right? Among all the possible values of u, okay? So v is fixed, u is changing. All right. What is the maximum value of the inner product? That's the length of v. Okay. Okay. And so we can conclude that we can conclude that the maximum value of u time dot v, okay? And under the assumption where the length of u equals 1 is a norm of v, okay? Okay, under that illustration, under this illustration, okay? And it occurs when cosine theta equals 1, okay? The maximum value, yeah, and it occurs when theta equals 0, right? Because, right? That means u is in the same direction. U has the same direction as v. V is fixed, okay? We fix a v, but we let u changes. Okay, so this is a v, okay? This is a v. And that's a u, okay? The u are all the unit vectors, so I can draw the circle. Among all the values, okay, this is u, the length is gonna be 1, okay? And then the inner product, okay, the value in the product changes only when in that direction, the inner product has maximum value, okay? In other directions, the inner product is smaller than them, than the value of that in that direction. This comes from the this above formula for the angle. Okay, that's the angle. Okay. All right, so that's a picture. So how about the directional derivative? For the directional derivative, okay, remember, the directional derivative, okay, at that particular point is going to be the gradient of f. I'm sorry, this is should be directional derivative. So directional derivative at that particular point is going to be the gradient of the derivative, which is a vector, right, times u. Okay, so if you assume the direction has a unit, we always use unit length, okay? Then clearly this is going to be less than or equal to the gradient of f. Okay, so here we are assuming, right? Right, and then equality holds, right, when the u is has the same direction with the gradient. Okay, so how can I say that u has the same direction with gradient? So when u equals gradient, you normalize it. Okay, so that's a unit vector. It must be unit vector, right? Okay, so that's the idea, right? So let's solve a problem from the book. We just want to know in which direction the derivative has maximum value. When we say direction, we usually mean unit vector, okay? Direction can, it's a unit vector. So we find here's a point. Yeah, we're trying to find the direction in which the maximum rate of change occurs. Okay? So this is a complicated question. Find the maximum rate of change of f at this point at the point 1 and 0, right? And there's a direction in which it occurs. Here's a function. And that is going to be sine x and y. So, so rate of change in direction u is going to be the direction derivative. Okay, so I'm going to find the gradient. You have to find the partial derivative first. It's going to be cosine xy. When you differentiate, you get y value. Okay, then fxy. When you differentiate, you get this is y, right? Okay. So the gradient of the function at this point is going to be when x is 0, 1, y is 0. So it's cosine 0. The product is always 0. So it's going to be 1. I think when when y is 0, x is this is going to be this is going to be 0. That's going to be 1. Okay. Yeah. When x is 1, y is 0. Okay. So that's a direction derivative. Okay. And so that for an arbitrary vector, unit vector u, right? The directional derivative at that particular point is going to be 0, 1, dot, and b. So the h is just a variable b. The problem is, what is the maximum value? B cannot be, I think it's clear. A unit vector means a squared plus b squared equals 1. So the maximum value for b is 1. Okay, so you can see the direct, yeah, it's always less than equal to 1. Okay, when equals 1, when b is 1, and then a must be 0 in that case. Okay, so so you can see that, right, without using above formula, you can tell that the maximum value of the direction derivative is 1, and it occurs when b is 1, a is 0, then in the direction of the y-axis. Okay. Right. Similar problems can be done for the three-dimensional. For the three-dimension for function 3 variables. Similarly, for function with 3 variables, okay, the direction of a derivative at the particular point, right, is the gradient, right, and the dot u, okay, and here u is a, b, c is a unit vector. You only consider unit vector, okay. So the length of u is a squared plus b squared equals 1. So we want to know when this direction derivative has maximum value, and we have the similar property. Okay, this is going to be less than equal to the length of the gradient. Okay, for it's always true for any unit vector. Okay, and then equality holds. This is going to be only when u has the same direction of the gradient. So then that is going to be the gradient of the function. You normalize it, okay? Because you have to assume you use a unit vector, so you normalize it. So it's a very similar That means it's in 3 variable, in 2 variables the same. Okay. So in order to find, let's do one more exercise, and we're going to take a quiz. Okay. So here's a let's see. So here's f of x, y, z. Okay, and then you get x. Okay, you get x and y plus 2z. Okay. Okay. The point is when and when and when. Okay. So we want to find out the maximum rate of change of y at that point in, and then also find the direction it occurs. Okay. So the gradient of f. Okay. I have to find the partial derivatives, right? So let me find the partial derivatives and evaluate. Okay. The partial derivatives, not the first one, it's easy to find out. It's just 1 over y plus 2z. The second one is I need a, I just write down this answer. Okay. And the third one, it's going to be 2x y plus 2z squared. Okay. So those are the 3 partial derivatives, and you evaluate at that point. So the gradient of this is going to be when both are equal to 1, so 1 over 3. This is negative 3 squared, so 1 over 9. And here's negative 2 over 9. Okay. Right. So that's what we get, right? So that for an arbitrary direction, the gradient of the direction derivative is going to be the dot product of this. Okay, A, B, C. Okay, so here this is a U. Okay, from linear algebra. Okay, and here we use as the length of U is going to be 1. We assume that. Okay, otherwise this can be arbitrary large number. Okay, we restrict it to the circle. To the U, the length of equal to 1. The length of equal to 1. So according to the above argument, this is always equal to the as less than equal to the gradient. Okay, so the gradient. Okay, which is going to be the square root of 1/3 square minus 1 over 9 square plus negative 2 over 9 square. Now you can simplify it, okay? So what you get here, I think I can take a 9 out. Yeah. Okay, so that will be 1 over 3 can be viewed as 9 over 3, okay? 3 over 9. So 3 square, 1 square, 2 square, 9 square. So you can take a 9 out, and 9 plus 1 is 10, 10 plus 4 is square 14. Okay, so that is going to be the maximum rate of change, right, of f at that point. And when it occurs in the direction, the unit direction. Okay, let's write down. Okay, it occurs at the unit direction. So I have to divide by the norm, right? We already calculated the norm, so it's going to be 9 over square 14. Okay, so that's the direction. It occurs in that direction. Okay, this is unit vector. Okay, usually when we're talking about direction, we have to say that's unit vector. We assume that's unit vector. Okay, now it's clear. Okay, among all the directions, the direction derivative is always less than or equal to square 14 over 9. And in this particular direction, which is the gradient, okay, which has the same direction as the gradient of the function, the rate of change of f, which is the maximum value. Okay. All right, so that's all for today's class. Lots of material. I hope you find the time to digest it.